right, and I would like to introduce a friend of mine who's going to be giving a talk to us this afternoon. His name is Istvan Lengyel, and he has a PhD from Kossuth in Hungary. And I've never been there. It's a little far away to go visit regularly. But it's a beautiful city from what I can see. He got his PhD from there, and then through a cooperative program came to the States, to Brandeis University, and also then MIT, right?
Yep.
And worked in all kinds of neat chemistry, but since then he's gone on to even other things. He works for Dow Chemical now, he's been there 11 years or so. We didn't overlap, but it was close. He has worked in theoretical and experimental chemistry, and has worked to marry those two areas together inside his work as an industrial chemist. He's worked on physics, chemistry, biological systems, obviously a lot of chemical plant production, chemical product, definition and design. So it's a very broad set of things he's worked on, and he's published multiple papers since here in various journals in various areas. All of those that I named, for instance, physics, math, chemistry, and material science. And he's offered to come talk to us today about some of the computational tools he uses to help solve industrial problems. In the last 10 years or so, computational science, and computational chemistry especially, has become a full partner with experimentation to solve problems. And he's here to tell us about that. Dr. Lengyel?
Thank you. Thank you. So the Dow Chemical company is one of the largest in the world, actually second largest as I believe. It has 50,000 employees and distributed all over the world, started from Asia, Europe, North America, South America. We don't have many plants in Africa, but as economy will develop in Africa, I'm almost sure that Dow will be there. So the products what we make start from basic plastics like polyethylene, polypropylene, going through common chemicals, whatever we use in plastic bottles and such, and going to the defense industry. Some of the materials which are used in fighter planes, windshield and the windows of fighter planes are very special chemicals which reflect infrared radiations differently than you would expect on a normal glass. And in terms of detection of those, it's important. So these are high-value materials. So in the past few years, Dow has been moving more into these specialty chemicals comparing to the commodity plastic-based. At the moment, Dow owns both of those businesses with large number of people and lots of debt. And one thing what certainly they would do is reduce the debt. And it will move the direction to get more specialty and less basic chemicals. Now, in any way, I joined Dow 11 years ago, and over these past 10 years, I could see quite a bit of change, what happened within Dow and in the chemical industry in general, in terms of application of computations and specifically computational chemistry to solve problems. So when the chemical industry developed about 30, 40 years ago very rapidly, everything was built very, very fast. The reason for that was that there was no need to optimize something because everything could be sold right away. In the past 10 years, however, as the industry became more and more developed, getting an edge on competitors and competition and making things cheaper, cleaner, and doing it faster became very important. So this was the time when computations became common. In the area of biology, that was probably in the beginning of the 90s, and that is phased out. Now in the chemical industry, it is pretty much in an upcoming stage, and in the biology and in the pharmaceutical industry, it's a boom again in terms of computations. So what happens with computational chemistry is that it helps to go down to the basics, the very basic event which happens with molecules when we do transformations on them, rearranging bonds between atoms, what a chemical reaction really means. So what we do is that in order to describe a chemical event, we start thinking rationally. And when you think rationally, you will see also what happens, what else can happen to the molecule in a given environment. So you look at the process from a mechanistic standpoint rather than put together things randomly and look at what comes out of it. So when you start thinking, that is always better because you will get to the end faster. So that is where computations greatly help. And when you design something with the full knowledge, how to make the chemical and what kind of byproduct forms, that will help you also to eliminate problems because you get a better understanding. So we are aiming not just simply for results which would describe something, but that also can predict. That is very important, for example, in catalyst design. So when you have a certain catalyst which works, you would like to even get a better one. How would you do that? The first thing is you try to understand what is the action of the catalyst, how it reacts with possibly the partners, opening lower energy pathways between the reactants and products. Now, if you think about your academic work and what the industry does, one of the main differences, I believe, is that here in the academia, you try to learn as much as possible. What it means that you try to do everything on your own. Now, in the industry, that would be kind of costly because of the time involved. What happens is more collaborative work, more specialized, people are more specialized in their area. However, they talk more with each other than what you would do in the academic environment. So that helps also in terms of the timing, because you can cut. What I saw at MIT, for example, to build up a laboratory reactor system with all the controls and data collection system and such, for a graduate student took about a year. Now, when I moved to Dow, one of the most eye-opening things was that to build a similar system took 1 month. And 2 or 3 guys worked on it only. They didn't have to learn everything. They already knew where to get the resources, how to build it up. So the development time is very much shorter. Now, another important thing is that when you present your data and you talk with your professor, many times talking in numbers is perfectly fine. Now, in a corporate environment where maybe the bosses did not really necessarily do science and did not do simulation, but versed in business, how you present your data to them is very important. So how can you convince them, and even how they can convince their bosses about funding and which direction to go. So communicating the results is kind of more important. And one of the lucky thing, oops, let's go back. One of the lucky thing is that when you think about the problem what you work on, if you work on a summer research project, you have a goal and you want to accomplish. Now, in the corporate environment, things are very similar. However, in problem solving, many times what happens is that there are multiple ideas. Here, it's coming from you or your professor, and you try to prove it, and if it doesn't work, you work more to prove it. Now, over there in the industry, what happens is that there are multiple hypotheses thrown around by many different people, and the issue becomes, if you have too many hypotheses, how would you decide which one is the right one? So eliminating one hypothesis of the pool of a large number is as good as proving one of them. Because whenever you start disproving things, it's enough to have one fact that disproves a hypothesis, but not how many that would support it. So one disqualification is perfectly enough to remove hypothesis from the list. And computational chemistry and computations in general is excelling in that regard, because we don't need to completely solve a problem, but need to disprove the validity of a problem. Now, an important thing is that whenever you do computational chemistry, we are at the molecular level, the smallest level what we work in the chemical industry. If you move to nuclear science, you will go to a little bit lower, but not much beyond. So how quantum chemistry and molecular modeling connects to different length scales and different time scales, I try to illustrate here. So we are working in the angstrom to nanometer range, moved up by a factor of 10 always. And the semiconductor industry is working in the 0.4, a few tens of nanometers range. In the past 10 years, they moved from here down to here, moved down by an order of magnitude. So they are at the mesoscale level, which means about 100 atoms scale, which is pretty small. Now, whatever things we can compute about a molecule has to be translated to these different length scales. Quantum chemistry on its own can give you qualitative information beyond the quantitative. So the qualitative, what a chemist generally starts with. Which side of my molecule is more reactive? You don't know necessarily how much more reactive. What you know is that it is reactive or not. But the engineer who does computations and the experimentation, whatever occur at macro level, like to see numbers. So what directly connects quantum chemistry to the macro scale is statistical mechanics. That is how you can turn vibrational frequencies, rotations of a molecule into internal energy, which means thermochemistry, heat capacities, heats of formation at a given temperature. The mesoscale is pretty much interaction of large number of molecules. When you have large number of molecules, all the atoms at the level of quantum chemistry cannot be really approached. So you try to figure out pairwise what is this interaction energy and translate it into the mesoscale. So what quantum chemistry does with the result of computations, try to feed information to higher and higher scales, and maybe does it directly, but the results will be used on the longest scales, like large reactor simulations and computing infrared spectra, what you can see in reality. Now, there are a few efforts in the academia to connect all these different levels of modeling in one single program, but that is not the case. Most of the trend and the most effective way at the moment is to feed computed information to next level of models. So mesoscale, for example, can compute viscosity. I give my interaction parameters, they predict viscosity, and viscosity goes into fluid dynamics modeling, where they calculate fluid flows in pipes and in reactors and in different equipments. So information through multiple length scales and multiple different modeling turned into macroscopically usable. So this is the level where, for example, lubricants for the engine can be optimized, and how to formulate a lubricant for a normal combustion engine. So computational chemistry as a whole, basically trying to understand chemistry by the computers, increased greatly in all branches of chemistry, so connected to biology, connected to engineering, catalysis, organic, inorganic chemistry. It is not really considered as a separate science. The really hardcore quantum chemists are physicists who develop new methods. What I will talk to you about is pretty much applied quantum chemistry and how you use it on other fields. One of them will be analytical science, predicting reactivities, spectral properties, and such. Now, I will show you in the next two slides a bunch of equations. You don't remember it. The only reason why I will show you to see how complicated it is and why quantum chemistry could be hard to not to learn, but to be effective and familiar with it, what methods is good for, or for what properties. So basically, quantum chemistry and molecular modeling will be to solve the Schrödinger equation, look at kinetic synergy of electrons, the nuclear interaction between the electron and the nuclei, electron-electron repulsion, and nuclear-nuclear repulsion. Thinking about an atom, you have a zillion electrons and less core, less nuclei. But to figure out how they move around each other and what are the possibilities, what is the minimum energy, is not an obvious task. So to solve these equations, they introduced a method which is called, to describe the wave function of an electron, whatever appears in the Schrödinger equation, by other functions. These other functions are considered to be primitive functions, similar to, like in math class, you can describe a sinusoidal function within a range by a series of polynomials. These are, as a polynomial is a basic function, you may use it to build up other functions from it. Now, we don't know really how the wave function looks like, so they try to describe that function with primitive functions. Now, one issue is that the complexity to do this integration is really hard. So there are multiple different approximations and methods, quantum chemistry methods, differ on how this issue is resolved or how they try to approximate what they neglect. The other is that how the wave function is approximated. So the wave function is a combination of a bunch of primitive functions, and how many primitive functions is used will determine how hard the problem will be solved. So going into the quantum chemistry computations, you will see a bunch of acronyms when you look at a paper. I don't want to go much into these acronyms, what they really mean. But the issue is that if you want to solve the Schrödinger equation exactly, you can solve it by hand for 2 atoms. 2 very simple things. But if you have 3 or 4 atoms, you don't do that by hand. It's impossible to do it. And by computers, to do it exactly, it is really hard. So what is N7 means that scales by the 7th power of the number of electrons. So doubling the electrons number, it will go by the 7th degree up, 7th power up. Whatever is practicable, though, are methods which are here. And the accuracy of these methods greatly depends on the molecules what you look at. So it is hard to judge. The point is that quantum chemistry, if someone doesn't tell you what is my accuracy, it could be a completely inaccurate computation. So looking at a paper, and when you see quantum chemistry computations, you should search for validation of some of the basic information, how accurate the computation is. And most of the time they compare heats of formation of molecule or reaction energetics. Reaction energetics is the one what basically tells more about the quantum chemistry and easier to compute than heats of formation itself. Now, what do we need to do? What do we need to know in order to do quantum chemistry? Quantum chemistry by itself many times is called ab initio quantum chemistry. What it means that you don't need any empirical data. You don't need to know how the molecule really looks like. You don't need to know what is the vibrational frequency or any physical property. You need to know only what type of atoms are in the molecule and what are connected to each other. Connection here means basically close to each other. So nature, when you draw a molecule, you draw a bond in between atoms. But nature doesn't know what you want to draw and will decide about it if there is a bond or not. So basically specifying the position of atoms is the initial state from which the quantum chemistry program will try to figure out what is the minimum energy conformer of the molecule. So you don't really need to know the exact structure, you need to have a good guess. And you don't need to know the complex arrangement of the electrons. The quantum chemistry will figure it out for you and tells you. Now there are other basic information which needs to be fed. Here I show you 2 possible isomers of oxygen. One of them is a singlet oxygen, the other is a triplet oxygen, meaning that here every electron is paired, here there are 2 unpaired electrons. And see from the electron distribution that they are completely different. So you have a double bond here between the 2 oxygens, and two free electron pairs pointing in this direction where you see the most red sign. In the triplet state, there is nothing like that. And by energy, I don't know if you know, but the triplet is more stable. So the oxygen, what we breathe in, is a triplet oxygen which does not have a double bond, even if books are drawing a double bond in between them. But this comes out from quantum chemistry very easily and takes a few minutes to do a computation like this. So what the task, what occurs for quantum chemistry computations, and I show what else can also be computed, are the following. Basically start with building a molecule, specify the method what you want to use, do a geometry optimization, and these are the basic things. I tried to put it in a different color. It doesn't come out very well here. It should have been yellow, and that would have been green. Now, after having a good geometry, you may do vibrational frequencies. Vibrational frequencies are important for IR spectra, and also if we want to do thermochemistry computations, the internal motion is important because it stores energy within the molecule. NMR spectra can be calculated easily. UV spectrum, which is not that easy, but after learning how to do it, it is very straightforward. If we have vibrational frequencies, we can have the infrared and Raman spectra. Raman spectra where you have symmetric vibrations and would not appear in the IR. So doing a high-level energy computation. Now, what high-level energy means is that if you have a good geometry, the energy may not be good. It is similar to the situation that you are walking in between hills and you are trying to find the position of the valleys in this field. You can locate it very well, but you don't know how deep it is. And when you calculate the energy, you try to figure out how deep that well exactly is. Now let's see what the structure can be used for. So I showed you on the previous slide a few things, what can be calculated, what can be computed, and in the next section I will go into what can be used it for in real life. So this was an interesting problem. I really loved it, not because if it was successful, because it was fascinating. So you can imagine that winter time, it is a problem if you have icing on the airplane wing. It causes that the wing, overweight and can break off when there are extra stresses. And also, if the weight is unevenly distributed, you have vibrations, and so the wing of the plane can break off. So you need to remove any kind of icing and sediments and contaminants from it. That's why you see in winter time that they go out and steaming the airplane wing and such. Now, Dow makes a fluid which is kind of strange. When you just put it on a table, it would stay like a droplet and like a piece of gel, doesn't move anywhere. But once you move it with your finger, it looks like water. So this is a fluid what can be used on the wing of the airplane to absorb moisture, and if you feed in salts, then it won't freeze. But when the plane takes off, because of the shear of the wind, it will just slip off like water from the airplane wing. So there was a problem with the zero shear viscosity of this fluid, and we had only 5 weeks to resolve the problem because the winter time was coming and we wanted to sell 100,000 pounds of fluid, and the customer was expecting it. So as we were the only one in the whole chemical industry who can make this fluid, we would have lost credibility, not be able to deliver. So it was important not just because of this product, but also other connected products what we sold to our customers. And up to the 3rd week, we did not have a clue what was the problem and how to fix it, up to the point that you tried to build up how the molecule looks like. And it was a very strange thing. When you look at it, was a polymer chain, kind of rigid, an acrylic acid methyl acrylate chain in which the pH was adjusted to about 7. So you have a bunch of negative charges along this chain. And when you have negative charges, they try to repel each other, so it is very inflexible, very rigid. And from certain distances, there were side chains on which hydrophobes were hanging off. And this hydrophobe looked like an aromatic system with a branched side chain on it. So these can have hydrophobic interaction only. And this was an ethylene oxide chain with whatever length. Now, another interesting feature was the fluid that a surfactant was added. We know that if you add surfactant to water, it will form micelles above the critical micelle concentration, and they form either spherical or rod-like structures. And the surfactant looked exactly like this guy, but was not connected to the polymer chain. So when the surfactant formed a micelle, I tried to indicate here with this little patch. Then the hydrophobes from the chains could incorporate into those micelles. So when you don't apply any force on this fluid, it looks like a three-dimensional extended structure with an infinite size of molecule. But when you apply a shear force and it tries to move the chains, it will pull out the hydrophobes from those micelles. So the viscosity will go down. Once you understood this, you know what to fix if the zero shear viscosity is not high enough. You want to increase the connectivity between the chains. You can do that by increasing the surfactant concentration, because you increase the number of linkage points, possible linkage points between different chains. And that was the only parameter what they left out from a design of experiment studies. You know, mathematicians worked on it for weeks and months before coming to us and designing the experiment from left and right and you know, doing it how fancy, and none of them fixed it. And the reason was because they did not know what to fix. That was the only parameter what they left out, and knowing it enabled them to fix the problem. So the next slide was a design of experiment studies, but no including the right parameter, and you can see the clear correlation and the changes in that parameter. So the next was that how to fix that fluid which is standing in a big vessel. It is not obvious, because if you try to mix it close to the mixer, you have fluid flow, but far away from it you don't, because this is a shear thinning thing, and far away from shear forces you don't have it. And apparently what our manufacturer used was a jet mixer where they accelerate the fluid and shoot into the big body, and fluid dynamic simulations were carried out to show if it's effective or not. It turned out not effective. So the guy who did the computations for the fluid dynamic simulation could figure out what velocity of the fluid and in what direction should be shot in that vessel to create a fully mixed mixture within a reasonable time. So by the 5th week, by the end of this whole study, everything was done and fixed. So see, the most fascinating part of the project was the molecular design. The person who designed it, he did not use quantum chemistry, he did not use anything, but I'm pretty sure that he had a good idea how this worked. So the size of this chain, for example, was done in a way that on an average, these hydrophobes could never reach each other. So they could incorporate only into micelles, which were floating around in the liquid. So he must have had a good idea and a good visualization how the molecule works and behaves. So for us, what it took to fix knowing how the molecule looks like, and that was fine. So this needed not very high level quantum chemistry, because the geometry and the sizes, even for a very simple computation, is pretty good. If you want to do energetics and such, it will be much harder, and you need more accurate computations. Now, the next thing, which is kind of simple to move from if you have a good molecular structure, is UV spectra. You would see this in the analytical lab. You like to see it because it's easy to detect, very cheap method for analytical. Quantum chemistry, in general, deals with ground state energies. But when you do a UV spectra and absorption of light, an electron will move, at least one electron will move from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And when we compute how the geometry looks like, we don't really concentrate on orbitals which are non-bonding orbitals for the molecule. So it's a little bit more challenging than just computing. But one of the methods, this is called Zindo semi-empirical method, excels in it if you had a good geometry. And what you can see on the bottom part is that if you had a flat molecule, I indicate here the angle between the two rings. So when it's flat 180 degrees and try to rotate, and we move to 90 degrees here, then the overlap between the orbitals of the two rings is less. And what it means that I'm trying to break up conjugation. This is a series of artificial computations, but what it illustrates for you is that if you have conjugation and overlap between orbitals, you have a longer wavelength absorption, and also you will have a higher molar absorptivity for that molecule. So considering what it takes to create a yellow color, you will need quite a long conjugation. 1, 2, 3, 4, 5. At least 5 layers of conjugation to move to yellow. To go to red or blue takes even longer conjugation. So when you see a colorful material like carrot, it takes quite a bit of length to create that long wavelengths for absorption. And what this can be used for? So one notorious problem in the chemical industry is that something has a color. Because color is created by sometimes trace amount of chemical at very low level, but high molar absorptivity, it is kind of hard to figure out. The most polymers, they use antioxidants, and these are phenol derivatives. And phenol derivatives, why we use it? Because they can be oxidized easily and forms a stable radical, which can capture other radicals, protecting the polymer chain later. But extensive oxidation and high concentration of the antioxidant will create molecules with high conjugation level, such as these two guys, and will create color problems. So many of the color problems seen in what I have seen either was associated with presence of antioxidant and overoxidation or presence of aldehydes. And this was an issue of aldehydes. When aldehydes are present in a mixture, they do aldol condensation. This aldol condensation is such that you will create carbon-carbon bonds. Basically, overall reaction would be to replace a CO group with that oxygen with another carbon from another molecule. So you build up a long chain. It happens in highly alkaline media, and especially will happen if there is a material that can dehydrate at the same time. And this was happening at a plant in Malaysia. And they had this issue for months. They were making, I think, ethylene glycol. And one of the byproducts, how they make ethylene glycol, is that they hydrolyze ethylene oxide. And the ethylene oxide is just an isomer of acetaldehyde. And if we have aldehydes in highly alkaline media, then you will have this color issue. So what the person who did the computations, one of my students at Dow, was created a series of these molecules and compute the spectra for each of them and try to recreate the observed spectra seen in the plant. So those lines, exactly 2 lines, one of them is the calculated as a sum of these individual molecule spectra, and the other was the experimental, what they saw. So what it helped them is to point out what is the position in the plant where the mixture could see the highest concentration of alkalinity, and try to reduce the alkalinity at that position, and it fixed their problem. So what we needed to do, give a proof of concept for them and convince them what to do at the plant. Can you do it without quantum chemistry? I'm almost sure that you can if you know what molecules form from aldehydes. Now, another thing what I wanted to show you is NMR spectra. So the molecules on the right side are kind of complicated. One of them is forms from an isocyanate and a carbodiamide. Carbodiamide is such that you have nitrogen, double bond carbon, double bond nitrogen, and the isocyanate is nitrogen, double bond carbon, double bond oxygen. So it is, you can make this compound that is pretty stable. And another one, this is an adduct of a carbodiamide and 2 isocyanate. And when these guys form, they form in an exotherm process and cause the problem because of temperature runaways. But what I wanted to show you how computations here help to deduct kinetics information from NMR experimentation. So NMR experiments were done in time on that reaction mixture and followed over a 20-hour period. And I used the computational information, the NMR spectra of the components, and create a composite spectra out of it and try to match the kinetics and figure out rate constants from that data, from the measured data. So basically, it did 2 things. One of them helped to identify components in a complex mixture, and the second was to extract kinetics information from the NMR. And basically, that way helped to build a model for the formation of these guys and describe the problem and help to manage equipment sizes and how to operate the plant without any incident. Let me know if you have any questions. Just raise your hand if you had questions to any of them. Do you have any up to this point? Okay, so let's go ahead. So another simple thing besides the structure, what comes out of quantum chemistry computation is atomic charges. These are partial charges assigned by a program, by an algorithm to atoms. So this was a chlorobenzene, and that was nitrobenzene. And what you would see is the charges on each individual atoms. So if you think about electrophilic aromatic substitution, electrophile, which is a positively charged fragment, in general, would go to the position which is most negative on the molecule. Let's see which positions are the most negative. Ortho and para position. So the meta is less. Now, what it tells us is that a chlorine on an aromatic ring would direct the electrophilic aromatic substitution to the ortho and para position. We know this in general from our general studies from experimentation. But quantum chemistry can help you not only in this very simple situation, but you may put multiple substituents on the ring and you can figure out which position would be the most negative, and that is where the substitution will occur by that thing. Look at the nitrate. In case of the nitrate, what comes out is that the meta position is the most negative, agrees well with our observation that the nitro group will direct into the meta position. Now, we may even compare the charges on the 2 rings. So this one is less negative than that guy. So would I expect that this one is faster or slower? I would expect that this guy is faster. In reality, that is not the case. So in just figuring out the directivity of groups, it was okay, but predicting the absolute rate constant, it was not good in that regard, because we know that the nitrate would react slower than a chlorine. Now we may go to a little bit more details. What I show you here is a few molecules. This was a toluene diisocyanate. I draw the molecule on the board. The second one is the HCl adduct. And the third one is the carbodiamide, what I was telling you before. I don't draw the whole molecule, just the middle part. So that is the bottom guy. And this one is that guy. And this one is this guy. So trying to figure out the reactivity to make those 4- and 6-membered rings, what I showed 2 slides back with the NMR spectra. When we look at the nucleophilicity can be associated with how negative a charge is, red means negative here, and also how concentrated that charge is. The more concentrated is a position, a charge position on a molecule, the more reactive it becomes. If the charge is spread around on a large surface area, it is not as reactive. So looking at the nitrogen and the oxygen, oxygen looks more red to me, but it is distributed on a large area. Nitrogen is nice and pointing, so that will be more reactive. Look at the other nitrogen. The other nitrogen is kind of hidden by that methyl group. It won't be that reactive as this guy. Now, here, a nucleophile reacts with an electrophile. Electrophile would be a positive part. We see here that carbon is a positive with the blue area, but it is not very pointy. It is not concentrated because it is spread around a large area. But here, you would see that this is a kind of concentrated positive charge. You have a similar from the other side, looking at from the bottom side too. So I would expect that this guy is a better electrophile than that was before, and this one is a good nucleophile. Comparing this guy reacted with that guy is less preferred than this guy reacting with that guy. Now, here again, we can see the 2 nitrogens of that carbodiamide. Nice and pointy nitrogen, and even more open to reaction than this one. So this would be more reactive, 2 of them close to each other. Either one of them can react, so the rate constant right away doubles. What we could figure out from these pictures right away, that we will have a nucleophilic attack on an electrophilic carbon atom, and it's more probable to happen when we have an HCl adduct, and even more probable if it happens by a carbodiamide. So 2 things. One of them was, if we have this guy appearing in our mixture will be more reactive. If we have HCl around, hydrogen chloride around, then it will behave like a catalyst because it will make my molecule also more reactive. Just from the pictures, you could identify right away basic principles, reactivity of one of the products, and also finding a catalyst for the mixture. We did not put this yet into a quantitative form in terms of rate constants, but that is possible too. for the specific projects I did it, and we built a full model, and that was used to figure out, you know, kinetics and equipment sizing for the plant. What else is electrostatic potential good for? One of my old friends, he retired from Dow a few years ago, did a very nice research on epoxides. So when you look at an epoxide, the reactivity will depend on the groups attached to it. If you put electron drawing groups on it, then the partial positive charge is increasing on that ring. So it will be more reactive. So he had an amine, and looking at the epoxide reactivity as a function of substitution, he could build up a nice relationship, and he could predict what the reactivity is and what would the rate constant be. Now, this was one of my first projects at Dow, and since I did this project well, that's why people are coming back constantly. And it was a kind of complicated business. So Dow makes polyurethane foams, and our customers came back to us after pulling their whole air conditioning duct system out that our foam smells like rotten wine. And they did not know, Dow denied everything, that we don't know anything about it, our material doesn't have any smell and such. But they went to an odor expert, and the odor expert knew about the wine industry, and he was showing that this molecule is the one which has that rotten wine smell. So they started analyzing their mixtures and components, and then they came back to Dow once more and telling that this molecule is in your mixture, is in your isocyanate, and we have a big problem here. And Dow was forced to pay for all the work what they did with their air conditioning duct system, buy back the material, and then the question was where it comes from, how we make it, can we avoid it, and how to avoid it. And this was a crisis situation. You can imagine that, you know, a plant which makes I think this was like 170 million pounds per year production, and all the income, whatever Dow has from it, was stopped. And was stopped for, I think it was like a month, just to figure this thing out. And when people came to me to, well, let's figure out how it forms and where it comes from, it was on Tuesday, and by Friday I could tell them what the rate constant for their formation, for its formation was, up to the parts per, to explain parts per billion concentration of the appearance of this guy. And the methodology was the following. So you had to know organic chemistry in order to figure out, and when you see this molecule, anisole is an activated aromatic ring, and the chlorine appears in the normal positions where it should be by an electrophilic aromatic substitution. So it had to come from chlorination, electrophilic aromatic chlorination of an aromatic ring. We don't know yet where chlorine comes from. We don't know yet what the catalyst is, because generally you need a catalyst. The only thing what you knew is what reaction type it is. So what I show you here is a building up a relationship. I show you how I build that relationship up between the computed free energy of an intermediate and the relative rate constant for chlorination of these aromatic rings. So I use this as a calibration data, and then for other molecules I figured out this expression, calculated this difference, plug it back, and I calculated what would be the rate constant. So for a large number of reactions, for tens and hundreds of reactions, within minutes you could calculate what is the relative rate constant. And the relative rate constant was relative to benzene. So the mechanism is the following. So for electrophilic aromatic substitution, you have an electrophile and an aromatic ring, and will attack one of the carbons of the ring, and will form a so-called sigma complex intermediate. The sigma complex intermediate is high in energy relative to the reactants and products, which will lose a proton to the media and creates the chlorinated molecule. So the trick here was that it is hard to compute activation barriers and it is not very accurate. But it is easy to compute stable molecules. And if I have and a stable molecule could be high in energy, but it is a well-defined geometry. So if it's high in energy, it is easy to get out of it. So we know that the barrier is small. And if we compare two different aromatic rings, one of them has a substitution on it, the other one doesn't, and if I compare the reactivity or the stability of these intermediates to each other, then the difference between the activation barriers will fall out almost, because the error, what I'm going to have, will be certainly less than this number. Both of them has a certain barrier, and when I take the difference, will be my error only the difference between the activation barriers. So this was a trick to turn a qualitatively not very good data into a quantitatively much better looking one. And that is what you could get out of it for relative rate constants. And this is just explaining, why I have to use the delta G, because I need to know the stability and how easy to get out, and that is determined by the free energy of the intermediate. So once you have that, whole sequence of reactions can be calculated, every one of them, and compare it with literature if those exist or not. This was one component, but there were, I think, 4 more components. And those 4 components could be chlorinated at multiple points again and compared to each other. So what it was telling that, this was accurate through 6 orders of magnitude pretty much, and could predict, started from hundreds of ppm going down to the parts per billion level. So Analytica figured out a method how to measure it. They measured, I think, 0.52 pp parts per billion concentration, and the calculations what I did showed 0.48 parts per billion without doing any experiments, basically. So here, computations, if you want to do the same by experimentation, imagine how many kinetics experiments you need to do and how many materials you need to prepare and isolate to go down to that level. Within the framework, time frame, it would have been impossible for the project. So basically, the thing what I wanted to show you is that computational chemistry is useful, and it is used in the industry broadly. I showed mostly for you applications to resolve plant problems, but the same is true for developing new products. So one of the projects what I have been working on recently is developing a thermal fluid that can be used in solar heat recovery systems. So when you concentrate solar energy with parabolic mirrors, you heat up something and possibly you create a steam and you recover the steam energy. And how high the temperature of that fluid can be, whatever is used as primary heat absorber fluid, is important, because the higher the temperature difference between the fluid and the recovery point, the steam generation, the better your yield becomes, because of this, the Carnot cycle, or the thermochemistry, how it works. So we have a thermal fluid which is used currently that works up to 400 C. But if you go up to 500 C temperature, then, then your heat recovery would improve by about 20%, which is a significant improvement. So there is quite a bit of effort. And what quantum chemistry can be used for here is that how to figure out which molecules are more stable at high temperature. Basically, it becomes an issue of bond strength. So the current thermal fluid contains biphenyl and diphenylene oxide. So if you think about when these two guys break, it will break here or break here. what can we make out of it? We cannot make a peroxide at high temperatures because peroxides would decompose anyway. So this guy can go and pair up only with that one. This one, what can it do? If it abstracts a hydrogen, would make a benzene, and you would make a triple bond on an aromatic ring, which is not very stable, so that doesn't happen either. This mixture is very good, but above 400 C it doesn't work. So how would it be possible to improve the bond strength of this guy, or maybe replace this one with something else that has better features? And it goes by bond strength, and what you do is by computational chemistry, you go around functional groups of the aromatic ring and look at the effect of functional groups. So one thing what certainly happens is if you put a methyl group on the ring, that won't help, because we create a benzylic radical which is very stable, easy to make, so decreases the thermal stability of the fluid. If you put a fluorine on the ring, a fluorine carbon bond strength is very strong, so that could be good. Maybe the person who would like to put it in their equipment won't like it, because if you put halogens and fluorine, those are kind of corrosive if they decompose and can eat up the equipment on a short notice. But that is one possibility. So by computational chemistry, you can go and test these ideas, investigate, and when you have a good idea that this would be good, you go to the experimentist and discuss, and she will do an experiment for you on it. And that is exactly what we did. So one young lady who joined Dow, she did the quantum chemistry work. I was teaching her how to use the computing facilities at the company and such, while at it. And by the end, we had a patent very recently, which patented a new molecule which would have higher stability and work pretty good at higher temperatures. Questions? Mm-hmm.
Thank you, Dr. Lengyel.
Mm-hmm.
Floor is open for questions. I know Dr. Lengyel would like to talk to you about any of the bits and points that we have here. Especially our chemistry majors over there.
So I did not talk much about the computational background. That is a fascinating thing. You know, when you have your computer at home, you like to tweet or do this, do that, go to here. But this computations needs powerful computers. And when you work with one molecule on a powerful computer, that is okay. But many times you have to work with many molecules pretty fast. So what Dow developed in the past 10 years, developed the whole computing infrastructure to deal with molecular modeling and also other type of modeling, and have clusters of powerful computers all around the world that can be reached from every location and run computations very efficiently. So one cluster is in India, another cluster is in Freeport, and the third is in Midland. Europe doesn't have a cluster, so whoever would like to do research and computations in Europe, generally they go to any of those other locations. But the internet and fast computers are pretty much spread out and can be done efficiently. Mm-hmm.
So you said that there were three different types of computational methods, like the Gaussian or
Yeah.
the pack. Where does ab initio and DFT kind of fit into that?
Mm-hmm. So all of these quantum chemistry programs can do both of them. The ab initio methods start with Hartree-Fock, and we'll go to deeper and deeper, while density functional, or DFT, density functional methods, they solve not exactly the same equations, but a translation of the original equations, and the same program can do both of them. So when you see Gaussian, Gaussian can do this, can do that, can do a combination of those, and can do a third one. It is more of all of the quantum chemistry codes can do a broad range of methods. And the hardest problem is basically choose which method you want to choose. So you want to choose the fastest method which is affordably accurate for the problem. So like you don't want to use Hartree fog for calculating a UV spectra because it won't work well. You can calculate, but the results will be wrong. And that is what comes with experience and learning of quantum chemistry. So getting to the point to be able to run a computation is kind of easy because you just have to draw a molecule and click on a button and run a computation. The harder problem is to interpret the data and knowing what method can be used for a given property.
I did have one back on the fixotropes that you were doing for
Yeah.
the airplane. You had a note up there about oil recovery, tertiary oil
Yes.
recovery. And I knew that some years ago Dow was looking at some of those materials. Are they really chemically related, or is it just two different chemical bodies that have the same sort of physical property?
So basically, learning how molecular structure and the associations affects viscosity helped us to have an idea how to modify viscosity of materials. So for enhanced oil recovery, when you think about it, what happens first is that there is quite high pressure and oil will come up to a certain point, but 20, 30, 40% of the oil is still down there in wells which cannot be recovered easily. They may be hidden between small pores of the rock, maybe they are in patches somewhere, maybe it is hidden under a layer of water, and what they try to do is secondary and tertiary oil recovery. So they use many times carbon dioxide to dilute the oil because the viscosity is very high and it dissolves very well in oil at high pressures. The other is they push water around, but as we know, carbon dioxide can escape on small channels where there is small pressure drop. What can you do to avoid that escape? And one thing what we worked on was to design surfactants that create foams under those environment down there, like 100 C temperature, higher pressure, and oil is present, to avoid the escape or lock the carbon dioxide into a certain layer, ground layer. The other way is that when you think about how computational fluid dynamics show this clearly, that if you have two channels, one of them is a narrow channel, the other is a broad channel, and you try to push a fluid through which has shear thickening behavior. What shear thickening is that at high shear, the fluid will have a higher resistance to flow. These are materials which have platelets in it, and those platelets try to, hit each other when you push it hard, then they won't flow very easily. So when you try to push this shear thickening fluid through, then wherever you have high velocity, you have high shear, so the viscosity goes up, and you have an opposite pressure against it. While the wider channel gets higher velocity, but the higher velocity will have an issue again to balance it out, because whenever the velocity goes up, then the viscosity will increase. So overall feature, choosing the appropriate fluid, you may force that the liquid will go through the small channel rather than the large channel. And these were additives and polymers what we were trying to make to help in removing oil from small channels. And the third approach to oil recovery is, for example, that there are certain type of rocks to which the oil is attached to, or certain oil attaches to a rock. That is not compatible if you start thinking, because oil is hydrophobic, while a rock, which is calcium carbonate, is hydrophilic. So how the heck hydrophobic can bind to hydrophilic? You have to have a binder. and those binders are surfactants. So those are partially oxidized large molecules, large organic molecules. And what can we do about it? Is it possible to remove them? It is possible to help to remove them with special organics that can bind both the hydrophobic and hydrophilic part of those surfactants. Once you remove, or you would be able to remove those surfactants, oil is naturally repelled from the rock. So the interfacial tension becomes low, so you can get it out easily. So there was quite a bit of effort in the past, and this happened since we learned much about the fluid and we started moving a little bit into enhanced oil recovery. So Dow now has products, multiple products, what we sell to the Gulf, and they use it for the purpose.
Didn't need a PP though, because it was coming out on its own, right?
Oh yeah.
Anything else? Yeah.
Uh-huh.
I had a question. So you've seen this progress of 10 years of computational chemistry go from, like you said at the beginning during lunch, you were telling us a few computers to having clusters of computers
Yes.
around the world.
Mm-hmm.
So what do you see being the new area, the new frontier for computational chemistry? What's the holy grail of computation? What kind of problems are you going to be solving in the next 10 years? Or 15 years?
So one thing is that it is guaranteed that computer speeds will increase. So you can do more accurate computations on larger molecules. That is especially important for thermochemistry and thermal properties. So one of the more affordable and highest accuracy method what we use is this G3 MP2 B3. It's a B3 LYP with combination of MP2 and the correction by the G3 method on these to get very accurate thermochemistry. And they are accurate to like 1 kilocalorie per mole on an average. So it is quantitatively accurate and good. 10 years ago, you could do maybe an 8-atom molecule. Today, it is more like 16, 20 atoms easily. So that will extend to larger and larger molecules, so that will certainly improve. Now the other is how to approach transition metals and how accurate quantum chemistry for transition metal complexes are. So in general, it is true that for especially thermochemistry, the quantum chemistry methods are not accurate enough. But once you try to figure out relative trends, they are okay. So that basis functions available for transition metals should be improving, and that would be one way to improve quantum chemistry. The third one is what happened in the past maybe 5-6 years, that linear scaling algorithms came in for the density functional theory. So what that means is that I show you that chart in which you had this 7th power on one. Let me go back a little bit. This one. So this scaling is kind of hard. Even the better scaling, the density functional theory is between 2 and 3. And the linear scaling means that you double the electrons and you double the computational time. Here you doubled it and went up by a factor of 8. And those are the cheap methods. So the linear scaling algorithms and the introduction and more widespread application and improvement on those can quite greatly help how large molecules you can compute. There is another direction that, for example, for enzymes or zeolites, for example, a reaction occurring in a zeolite cavity may be considered explicitly by quantum chemistry, but as you move farther and farther away, you reduce the level of theory. So whatever is farther away, you don't need to do it with that high accuracy. And that's another direction to improve and get to larger and larger molecules.
So have these more fundamental methods started reaching into polymers?
Well, polymers is a tricky thing. There is a way to go in there. With polymers is that there are two directions. One of them is polymer kinetics and making the polymer, doing the catalysis. The other direction is to to look at associations of polymer chains. And Dow started making, you can make copolymers. And these copolymers may be such that they are absolutely randomly distributed, or you can make it as blockwise. And these block sizes could be different and randomly distributed, or you can make it so that regularly distributed, very regular and very regular sizes. And Dow created a catalyst maybe 4 years ago, which does this random block copolymers in a very peculiar fashion, and the polymer what it makes has features what you have never seen with polymers. So for example, when these fragments are different and the blocks are different, the blocks will associate with each other between different molecules. So you can create localized, very highly organized sections of a polymer chain. So when they aggregate, they will make regular structures. They can make patterns of arrangements like hexagons or stripes arranged in 3 dimensions. So the polymer what you made will have color because you are working at the diffraction length scale. So when a light is shine on it, then you would see a color coming from the polymer without the presence of any color causing agent. So Dow is trying to sell it to the credit card industry because you can, I mean, Dow is the only company who can make it. And if you can make it, then you can do things what other people cannot copy. So you can put it in money. For example, if you make a little bit of paper money with plastic, that nobody else can really reproduce easily.
I have a personal question. Like, what made you get into computational chemistry?
Oh, okay. So I did my PhD in experimental physical chemistry, reaction kinetics, studying nitric acid oxidations, which had nothing to do with quantum chemistry. And now in kinetics, I moved more and more into computations and studying reaction diffusion systems. And when my advisor became the dean, I picked up his quantum chemistry class. And I was teaching from a physics book pretty much, which was really, really hard. And I hated it. So I didn't like to learn from it. I hated to teach it. But I saw the use of it. So when I wanted to move into more applied chemistry, I looked up groups, and one of them at MIT was interested in chemical mechanism development and molecular simulations. So I could, that was the point when I went more into computational chemistry, and by the time I got to Dow, especially within Dow, I do mainly computational chemistry. But before that, I did not do, I did much at MIT, yeah. I did there, but not before. So not during my PhD or anything. Started from experimentist and moved more and more into computation. Mm-hmm.
Mm-hmm. Well, let's thank Dr. Lengyel again for
Thank you. Mm-hmm.